Good morning, everyone. Today, we are going to see on the topic of managing Hadoop file using a MapReduce concept. So, I am Karthian, working as an assistant professor in the Department of Mechatronics at SNS College of Technology. So, by the end of this lecture, you should be able to explain how large-scale data is processed in a distributed environment. So, before we get to the MapReduce, let's quickly set the context. Hadoop is an open source distributed processing framework designed to handle massive volumes of data, what we call the big data. What makes it powerful? Three things. Scalability, you can add more machines as data grows. Cost effectiveness, it runs on commodity hardware. And flexibility, it handles structured, semi-structured, and unstructured data. So the Hadoop ecosystem includes tools like HDFS for storage, MapReduce for processing, YARN for resource management, and higher level tools like Hive, Pake, and HBase. Think of these as layers working together. So now, before we processing the data, we need to store it. That's where HDFS comes in. The Hadoop distributed file system, it is specifically designed for storing very large files across the clusters of machines. So three categories define HDFS. It is distributed, data is spread across many nodes, it is fault tolerant if a node fails, data is not lost, and it provides high throughput. It's optimized for reading large data sets in batch. The key benefits is scalability, reliability, and something called data locality, which means processing happens close to where data lives, saving network bandwidth. The HDFS architecture component we have discussed in the previous class. There are four key components. First, the name node. This is the master server. It doesn't store the actual data. Instead, it manages the metadata, the directory structure, file names, and the location of the data blocks. Second, the data nodes. These are the slave servers. They physically store the data and serve read or write request. Third, the client, that's you or your application interacting with HDFS to read or write files. Finally, the data is divided into blocks. By default, each block is 128 MB and each block is replicated across multiple data nodes, typically 3 copies to ensure fault tolerance. So even if one machine crashes, your data survives. So introduction to MapReduce, it is a programming model that allows us to process massive data sets in parallel across a cluster. The core idea is simple: divide and conquer. You split the problem, solve each part independently on different machines, and combine the result. The advantages are significant. That is parallel processing, multiple machines work simultaneously. Scalability handles petabytes of data. Fault tolerance, if a task fails, it simply restarts on another node. And high throughput, large batch jobs complete efficiently. The classic example used to explain MapReduce is a word count, counting how many times each word appears in a large document. MapReduce working principle. Let's walk through it. There are three phases. Phase one is the map. The input data is first split into smaller chunks. Each chunk is processed by the mapper function, which reads the data and emits key value pair. For example, in a word count, each word becomes a key value of 1. Phase 2 is shuffle and sort. This is the behind the scenes phase. The framework automatically collects all the key value pair from the mappers, groups them by key, and sorts them. So all instances of the word Hadoop are brought together. Phase 3, reduce. The reducer receives the grouped key value pair and aggregates them. For example, summing all the 1s for each word to produce the final count. The output is returned back to HDFS. Now let's see how a MapReduce job actually runs on a cluster. When you submit a job, the client sends it to the job tracker in older Hadoop or the resource manager in yarn-based Hadoop. The resource manager accepts the job, splits into a smaller map, and reduces the task and schedules them across task trackers or node managers on the worker nodes. Each task tracker executes its assigned task and reports progress back to the master. So a critical feature here is the task monitoring. If a task fails, it automatically reschedules on another node. This is what gives MapReduce in reliability. The job isn't complete until every single task reports success. And how we are going to manage the Hadoop file MapReduce involves two areas. File management in HDFS includes performing read or write operation, managing the replication factor for data safety, and handling block level operation. Job management in MapReduce means submitting job efficiently, monitoring task execution, and optimizing resource allocation. Some best practices to follow: always ensure data locality, schedule tasks on nodes where the data already exists. Optimize job configuration, tune parameters like block size and number of reducers. And always monitor cluster health and have a strategy to handle failures gracefully. This mind map will give you a bird's eye view of everything we have covered today. You can see how HDFS components, MapReduce phases, management practices, architecture, principal features, and benefits all connect to this central topic. Use this as revision reference before your exam or assignments. Let's quickly recap. We covered the HDFS architecture, name node, data node, and the client. We understood the map producing working principle like map, shuffle, sort, and reduce, and we traced the job execution flow from submission to monitoring. Looking ahead, the skills you have built today are the foundation for Apache Spark, which improves on map produce within memory processing. Keep exploring on the real world cases. That's where this truly comes alive. So, thank you.